the topic of this talk is really about identifying tasks at which low-depth quantum circuits have an advantage over low-depth classical circuits, and then associating with that advantage and a sort of an operational task or an operational use, which is the production of certifiably random bits. And then the whole result really has two components. One component is just tying off some open problems that were stated about separations between low-depth quantum and classical circuits, and the second component is about this certifiable randomness. I don't know how to increase the volume. However, I have another microphone. How about this? Is this a little bit better? Okay, good. All right, so I just explained the title, which I will explain again later, so I'm just going to keep moving. So this is joint work with between myself and Jalek Stark and Thomas Vidic, and I guess our affiliation list is a little bit long, but this work really was started at while I was visiting Caltech. Jalek was a student at Caltech, and of course Thomas is a professor at Caltech, and then also I'm a postdoc at the University of Waterloo Institute for Quantum Computing, so a good portion of the work happened there too. And for the rest of it, you can ask Jalek or I, or we'd be happy to tell you about it. Okay, so I'm going to move on pretty quickly to talking about the mathematical underpinning of these results, which, as I mentioned before, is really about identifying tasks for which low-depth or constant-depth quantum circuits actually have an advantage over classical circuits of constant depth, or even all the way up to, but not including log depth. And I'll mention later, there is a constraint that we place on on all the circuits, classical and quantum, which is that they have bounded fan-in. So they're only allowed to take, every gate in the circuit has bounded fan-in. So each gate is only allowed to take a constant number of inputs. And so I guess the study of this type of separation was really kicked off by this breakthrough result of Bravi, Gossett, and Koenig last year. And I'll just go ahead and state their result because it's really the inspiration for this work, and I think also other works that came out this year, including the talk that is immediately following this one here at QIP. And so their theorem states roughly, and I'll go through sort of an iterative refinement of these statements where we then get into open problems and so on, the problems that our work addresses. But the initial result says that there exists a relation problem, so I'll define what a relation problem is in a minute, that can be solved by constant depth quantum circuits, but cannot be solved by any classical circuit with bounded fan-in gates of sublogarithmic depth. So I'll say a little bit more about this result as I move along. To start off with, I'll say what a relation problem is. Many people might know what a decision problem is. So in a decision problem, you're given an input, which is an n-bit string, say, and for any language, assigns to n-bit strings a label, either a 0 or a 1, and you have to compute it. So it's a yes or no answer. So you could be given a bit string describing a 3-sat formula, and you have to decide is it satisfiable or not. It's a decision problem. A relation problem is the type of sort of computational problem that we'll be studying here. And in a relation problem, you're given an n-bit string, but you also output an n-bit string. And the success condition is that to every input string, there's assigned an allowable set of outputs. And the requirement is like if you have a circuit, if you have a circuit solving a relation problem, that means that whenever you give it an input, the output of the circuit lies in the allowable set. Okay. And I'll say at this point also that, so this talk is about comparing quantum and classical circuits. We will think of all of our circuits, both quantum and classical, as having classical bit string inputs and outputs. So the classical circuits have n-bit inputs and n-bit outputs. And the quantum circuits we just assume that we're giving them inputs in the computational basis, and we always assume that their output state is measured in the computational basis. So it may be probabilistic and so on, but they're always going to return an in-bit, classical bit string. Okay, so now I'll state the BGK, Bravi, Gossett, Koenig result a little bit more precisely, so I can talk about the refinements of it that we prove in our work. So just filling out this theorem statement a little bit more, it says that for every n, there exists a relation problem. So there's like a family of relation problems. And you could refer to this family as the 2D hidden linear function problem. Although I'll never actually describe what that is. We take a different route than that to construct our relations. But anyway, this family of relations has the property that for every n, the relation can be solved perfectly with a constant depth quantum circuit. And even actually, it's not even a fully generic constant depth quantum circuit. It's actually one that's composed of 1 and 2 qubit gates, and they have like grid-like locality in the way that the gates are applied. But on the other hand, so that's like a completeness condition, and on the other hand, there's a soundness condition. So the soundness condition says no probabilistic classical circuit of depth less than log n can solve this 2D hidden linear function problem with probability greater than 7/8 on every input. So it's a circuit separation. And one of the things that was really nice about this result is that it's an unconditional separation. So it doesn't require any computational assumption. We just know that there is a task that constant depth quantum circuits can do, constant depth classical circuits cannot do. So that was one of the things that made the community very excited about the result. There's a slightly different thing that made us in our work really excited about this result. Of course, the thing I just mentioned, but also that at the heart of their proof is about circuit separations is a non-local game. It's called the GHZ game. And if you've never heard of a non-local game, I'll touch a little bit on it later in the talk. I'm not going to discuss it too much. But the point of non-local games in this context is that they provide a separation between an information theoretic separation between non-communicating players who play this game, which are classical. If they're classical, they can't perform as well, and if they're quantum, they can perform better. So it's like a separation in the information theory world that gets ported over into this separation in the circuit world. And in particular, the Bravi, Gossett, and Koenig argue within their proof, at a high level, they basically say that if you solve the 2D hidden linear function problem perfectly with your constant depth circuit, then in some sense, your circuit is also playing the GHZ game perfectly. And that's something we know that you can't do classically if the players are non-communicating. So I've put quotations around this because you have to make precise exactly what you mean by that. In non-local games, there are players that can't communicate. In a circuit, there are no players. They're just inputs and outputs. But in some sense, they've found locations within the circuit that act like non-communicating players in the GHZ game. And this is how they actually get the completeness and soundness conditions that they do. So for the GHZ game, the completeness is 1 in the quantum case, and the soundness is 7/8 against classical provers. So they sort of have like ported over exactly this completeness soundness into the circuit world. Okay, so myself and my co-authors have worked a lot on non-local games, and if you've seen the non-local games literature, there's like a natural idea that sorry, I'll go back. There's a natural idea that this bottom, kind of proof flow brings out, and that is just repeating it here. The BGK result says a low-depth circuit solving this relation implies some sort of GHZ separation or saturation, meaning they're playing the GHZ game optimally. But we know in the theory of non-local games that if you have players which can play GHZ optimally, or maybe some other non-local game like CHSH or the Magic Square game. I'll say a little bit later what CHSH is if you've never heard of it. But anyway, the point is if you can play these non-local games nearly optimally, then we know you can do all sorts of other operational tasks with an information theoretic security guarantee. So this is like in multi-prover interactive proof setting. And we know that you can do things like amplify soundness, that you can have, in a sense, a form of average case hardness, and I'll describe in the next few slides specifically what I mean by these things. We also know that you can do perform a sort of cryptographic primitive called randomness expansion, and you can even do much more complicated things like verify quantum computation with a multi-prover interactive proof with entangled provers. So we know you can do all of these things, and so in some sense it was just natural to ask, why can't, if you can design a relation such that solving the relation implies GHZ saturation, with quotations around the GHZ game, why can't you design a relation which implies all of these other things, but sort of also in quotations, right? But it has much better soundness, and it has average case hardness, and randomness can perform randomness expansion in some sense, and so on. So this slide is sort of a roadmap for the way that we were thinking when we worked through this result, and it also is like a high-level statement of our results, because essentially the statement of our results at a high level is that we do the first three things. So we show that you actually can get better soundness. You can get what's called average case hardness, and you can perform randomness expansion in this model. And then the third thing, I've put the third verified quantum computation on the slide just to illustrate that there are many other things out there in the non-local games world which maybe you could bring over. It's not even clear to me how to make sense of that question. It's very open-ended, but what would it even mean to port that over into a circuit separation? But the first three we figure out, and the last one is kind of left as a thought experiment or something. Okay, so this is like the high-level description of what we do, the three in green there. And so now what I'll do is define each of these things. I'm actually going to define, when I define what I mean by soundness amplification and average case hardness, I'm going to lump them together because it saves time and it sort of gets to the punchline faster. And then I'll later say what I mean by randomness expansion. Okay. When I talk about soundness and average case hardness, what I'm really referring to is two parts of the, so this is the original theorem statement from the Bravi-Gossett-Koenig paper. And completeness is all good. So family of relations can be solved perfectly by constant depth quantum circuits. And then the part we'd like to address is actually part of the soundness condition. So the first thing is the quantity soundness itself, which is this 7/8. So saying that a classical low-depth circuit shouldn't be able to succeed more than 7/8 of the time. It would be nice if we could make that number smaller. That would make a bigger separation between the quantum circuit and the classical circuit. And then the other thing is this, quote, average case hardness, which just refers to this, that this soundness condition is saying you can't succeed. It's saying it is not the case that a quantum circuit can, a classical low-depth circuit can succeed with probability 7/8 on every input. But there are many inputs, and so if you wanted to separate quantum from classical, you might have to test every one then. But the inputs are n-bit strings, so there's exponentially many of them. You may not want to have to test every one. So what I mean when I say soundness amplification or improvement to exponential soundness and average case hardness is just the following kind of addendum to that theorem statement, which we prove in our work. So all it does really is change the soundness condition, and it says that instead of, I'll go back, instead of the soundness being that you can't succeed with probability 7/8 on every input, it says that if you sample from the appropriate distribution as your input distribution, you can actually design relations where the classical low-depth circuit, well, the quantum low-depth circuit can still solve it perfectly. And the classical low-depth circuit can't solve this instance with probability higher than exponentially small in n. So that's exponential soundness. The original soundness condition, I mean, this is fully qualifies as a circuit separation, which was the goal of the authors. This is more like thinking about if you wanted, I guess, to test devices in the laboratory, you wouldn't want to test them on all inputs. You maybe would just want to test them on a few sampled inputs and already know that there's a separation. So that's maybe what this would allow you to do. Okay, so that's what I mean by...
But it's not, in their case, you have to test all inputs.
yeah, so this average case hardness business, which now I've lumped together with exponential soundness, comes for us for free, essentially, by unpacking their theorem statement. So, and I'll say that later on in the, yeah, in a sense you could say that they just already had average case hardness. And actually when we wrote our paper, we didn't say anything about average case hardness at all, but later papers did, and so we put it in. Right. But this exponential soundness business, so I've lumped them together here, but this one should also be easy, but isn't immediate. And hopefully if I have time, I'll get to why it's not immediate. So it's not immediate, but you can ultimately do it. Right. But there's like a very simple intuition for how you should be able to do it. Doesn't work immediately. Okay. Okay, so that's these two. And the next part is about randomness expansion. Yeah.
In their case, what they actually do is they sample from some set, which it's enough that you have a few samples to know that the circuit succeeded, right? It's not.
So.
It's a verification. There is a way to verify.
You can summarize the question.
Yes. So the question is basically whether the Bravi-Gossett-Koenig result, this one, already essentially doesn't require this on every input. Like it's already has average case hardness, so good question. My interpretation is that they've packaged this thing in this algebraically nice 2D hidden linear function problem. There it is. And my impression is that the 2D hidden linear function problem doesn't have this property because the part where you encounter the GHZ game is only like a very small fraction of all the inputs. The part where you actually encounter the GHZ game does have this property. So in some sense, if you defined your relation to like throw out the beautiful algebraic packaging that they had and just take the subset of it, then you would have average case, and that's all that we do for that. The soundness part was more of our focus. Okay, let's see. All right, so now I'm going to talk about what randomness expansion is, and hopefully what it means in this model of low-depth circuits. But the natural starting point for randomness expansion is in non-local games, and I should say a bit about non-local games too, because that's sort of where our intuition is coming from. So what I'll first do to discuss randomness expansion is tell you about like the canonical non-local game, or the most famous one, which is called the CHSH game. I'm going to use this interchangeably in this talk with every other non-local game. So if I'm talking about a game, just think about this one. And I also won't have time to go through in detail how this works. But for the purposes of this talk, you should think of a non-local game as an interactive proof between a referee, a classical referee, so that's us, and who's testing two players, which will later become two black box devices. And the referee wants to test, well, the referee is essentially trying to test the players for some sort of entangled or quantum behavior. At least that's the viewpoint that we're going to take. And so they need to design a game. So the two players are cooperating with each other. They're adversarial against the referee, but they cannot communicate. Alice and Bob cannot communicate during the course of the game. So those are like the most important things to remember. And then the content of CHSH for our purposes is that you can design a game. A game consists of the referee sending inputs to the players, and the players then, without communicating with each other, sending back outputs or responses. You can design a game where the referee randomly samples bits as the inputs. Alice and Bob respond with bits as the outputs. And the classical winning probability is at most 75%. So this is the case in the CHSH game. And yet, and this is like Bell's inequality, so this was early in the history of quantum mechanics, this was discovered. There is an entangled strategy, so a strategy in which Alice and Bob each have qubits, and those qubits are entangled, and they measure the qubits in a particular way according to the input that they receive, and return their measurement outputs as responses. There's an entangled strategy which wins this game about 85% of the time. So more than you could win it in a purely classical world. And so I won't dwell too long on the CHSH game. This is just like a little tidbit for anyone who's never seen non-local games. In our context, or to motivate randomness expansion, the way to describe this is like an interactive proof against untrusted provers or players or devices maybe. An interactive proof for entanglement or for quantumness. If you play this game many times with Alice and Bob and they win much more than 75% of the time, you start to think that maybe they must share entanglement. They can't be purely classical, right? Okay, and so this is like the motivation behind randomness expansion. The actual statement or idea of randomness expansion itself, so this was proposed by Roger Kolbeck, and this is an idea for testing untrusted random number generators that come in pairs, like Alice and Bob in the CHSH game. So Kolbeck said, the CHSH game is kind of like a test for entanglement, but in the optimal strategy for CHSH, we know that players must measure a quantum state, and when they measure the quantum state, their measurement outcome should be random and should have inherent randomness, like separate from everything that's happened before. And so maybe you could turn this interactive proof for entanglement into an interactive proof for producing randomness. Or in other words, maybe you, the referee, so that's the guy with the stopwatch, you could start with a small random input seed, and you could use this seed to design inputs to a bunch of rounds of some game. So you send the inputs to Alice and Bob, they send you back the outputs, you write them down, you keep doing this. Say this is the CHSH game. It doesn't have to be, could be something else. You do this many times and you record it all in a table, and then you have some test on the output. So in the very sort of base model of randomness expansion, your test would just be that they win CHSH much more than 75% of the time. Okay, and you would like to be able to prove, and indeed it can be proved, and there have been many refinements of this idea, but that if these devices pass this test, you know that their output has high min entropy, so it has a lot of randomness, even conditioned on their input. So this is assuming you know the devices have not communicated with each other for this entire time. All right, and it's also the case that, sort of honest quantum devices could always play CHSH here, and if they did, they would pass the test. So honest devices can pass the test, or an honest random number generator could pass the test if it had the appropriate capabilities. Oh, sorry. And that means that if your random number generator fails the test, you just abort, and you say, I don't trust this random number generator anymore. It didn't pass the test that the honest one would have passed. Okay, so that's the idea of randomness expansion. This idea has been heavily refined. So when Kolbeck started out, he could show that if you started with n bits of randomness, you could produce n more, or maybe 1/10, 1/100th of n more by doing this process. but after a while, I'm just going to cite one result. I don't have time to go through the whole literature, but after a while, it was discovered that if you de-randomize the input seed appropriately, you can kind of bootstrap an n-bit random seed to begin with and design a bunch of inputs to many, many rounds of CHSH. And you have to have a more complicated test as well. But if you do all of this, you can actually get a guarantee where the output entropy is exponential in the original input entropy. So whereas before you started with n bits and you got like 1/100th of n more, now you could start with n bits and maybe like in one shot kind of produce as much randomness as you would ever want. Right. So this is actually not the state of the art of randomness expansion. It goes beyond this even, but this is what we're going to sort of keep in our heads as the most concrete state of the art statement. Okay, so that was a description of randomness expansion. And now there are two parts left in the talk. One is a non-mathematical part. That's about a sort of physical principle that we're proposing in parallel to the actual mathematical results. The second part is a discussion of the technical work, which I may run out of time for, but I'll probably end up like breezing through it. But so let me first discuss this physical principle. So this is the idea that that our results, if you believe a certain physical principle, show that you can actually have a single device test for producing randomness. So just like randomness expansion before, except it removes the requirement that you have two non-communicating devices and that they share entanglement and so on, which is nice because that's maybe a hard thing to do in the laboratory. So we'd like to do some sort of exponential expansion where we are guaranteed that this output has high entropy, but with only a single device somehow. And so this circuit separation type of result that we prove with randomness expansion can accomplish this if you're guaranteed that this device is low depth in some sense. Okay, so that it's either a low depth classical circuit or a low depth quantum circuit. So this translates this scenario directly to our actual mathematical result. So, I mean, in some sense, that's unsatisfying because, we wanted this to be a black box test, and if you have some promise that your device is low depth, that's not really black box, right? That's some promise about your device. So this is where the physical principle comes in. This is not about mathematics anymore, but how could you imagine, just for fun, how could you imagine enforcing such a constraint, right? And the idea is this, like maybe, what if you just time how long the device takes to solve this problem, and you just say, well, maybe there's some like ultimate limit on how fast a classical gate can be performed. Okay, so like you have a gigahertz processor, so you can do it in 10 to the negative 9 seconds, maybe. And also, apparently, quantum gates are actually surprisingly fast. That's a 10 to the negative 7. So they're maybe like 2 orders of magnitude slower than classical gates, faster than I realized. So the intuition is that if you just time this device and it takes t seconds to solve a relation problem, then in that time you could apply a quantum circuit of depth 10 to the 7th times t. So every layer of the quantum circuit takes 10 to the negative 7 seconds. So that's like how if you're sort of doing true parallel computation, that's how it would work. And so, but by the same principle, a classical circuit couldn't apply, or a classical machine couldn't apply a circuit of much greater depth, right? Maybe it could get up to like 10 to the 9th. So then you figure that, well, either this device, if it's solving the relation this fast, it's either a quantum circuit of this depth or a classical circuit of that depth, right? And so then, if you buy this physical principle, then it's sort of sufficient to have a test which separates the power of depth d quantum circuits, and depth like 100 times d classical circuits. We do that because, just like the Bravais-Gosset-Koenig result that we build on, we separate constant and log n. So if you make n big enough, you get this separation. Okay, so it's the end of this sort of physical principle part of this. But it's just to kind of highlight that we're trying to, like this is maybe the easiest way to understand the statement of the result that we're trying to, that we prove. How am I doing on time? Okay. Yeah, so I should, right, so this just says again, if you believe this physical principle, then we actually have a test of this type. But we have to assume that principle. And since I've gone through all this discussion of verifying randomness from a single device, I should also mention that there's another result that came out this year, which at a high level seems similar, but when you get into the machinery of how the proof works is completely different. But there's another result which does certifiable randomness from a single device. The difference between them and us is that we require this physical principle that I just described, which is in a way sort of cheating. But on the other hand, I'll describe in a second why it might be interesting. They don't require that. So their protocol is more black box than our protocol. They only require a standard assumption in cryptography that the learning with errors problem is hard for quantum computers. Okay, so that's just to avoid confusion. And there's I guess here I'll say the one potential advantage of our results. There's a trade-off. Their result is more black box, as I said. But ours, in ours, the completeness side, the quantum circuit which passes this test, is easier to implement. So it's the constant depth, and can even it's like even a Clifford circuit. Okay. So that's the end of the physical principle part of the talk. I have, 3 minutes left, slightly less. Maybe what I'll do is, let's see if I can breeze through the technical part of, okay, I'll tell you a couple, I'll tell you sort of one technical takeaway. So the technical part of this work comes in dealing with these quotation marks around GHZ. So what does this even mean to have a GHZ game embedded in a constant depth circuit? And it turns out that part of what that means is instead of a GHZ game, which has 3 players, the 3 red dots, and the state for the optimal winning probability, or optimal winning probability is a graph state that's where the graph is like a triangle. You use what's called a stretched GHZ game, and the Bravais, Gosset, and Koenig use this thing. And I think it even comes from earlier work, too, that this exists. In this game, there's still 3 active players, but there's also a passive player at every one of these nodes. And I won't describe what they do, but in a sense, the main point is that it has same completeness and soundness as GHZ, and yet the graph state that is the shared state that the players have to share is stretched out. Okay, and we find it useful in our work to be able to stretch games in a different way. So in pictures, this is the old way. This is the way that we stretch games. And we can do this for any stabilizer game, actually. So from now on, I'll talk about magic square. And we use let's see. OK, 1 minute. Maybe I'll just say the key takeaway, which is that the key property of these stretched games is that no matter how far you stretch them, the shared state to win with the optimal probability is still preparable in low depth, with a low depth quantum circuit. And that, I'll just click through these slides. We use that to construct a relation problem. It's analogous to the way that Bravais, Gosset, and Koenig construct a relation problem. But for exponential soundness, there are some technical details we have to overcome. Same thing for randomness expansion. We have to de-randomize the input to this relation. And OK, so that's it. There's some related work, which I don't have time for, but the next talk is one of them. And that's it. All right.
Okay, we're a little low on time. Is there maybe one quick question? Yeah.
Where is it? What do I do?
So I'm very confused by the statement that you can do this with a
purely classical circuit, because classical circuits can only make pseudo-randomness. So how is even a depth 100 T classical circuit supposed to certify that it's expanded my randomness?
So the classical circuit cannot pass the test.
Oh.
So that's the. I'm sorry if that was.
It sounded
confusing.
like you said either one could pass the test.
It can certify the answer.
Yeah. There are two things. There's the device you're testing, and there's you, the referee, who then does some computation on the output of the device and the input together. So that computation is classical. That's like the test, but the device that's the test that the referee applies to the device. But the device itself has to be quantum in order to pass the test and has to produce randomness.
Okay, good.
So that's the, yeah.
Thanks.